Welcome to the basic fundamental lecture on electrical machines. We are going to discuss the fundamentals on motors and generators. This is with respect to the first year BTech Basic Electrical and Electronics portion. We'll start our discussion with electromechanical energy conversion. What is electromechanical energy conversion device? So a device or a machine that basically converts the electrical energy to mechanical form or vice versa, that is mechanical to electrical form, is known as electromechanical energy conversion device. A DC machine, so when we talk about DC machine, we talk both for the generator as well as the motor, is an electromechanical energy conversion device because it will convert the energy from one form to the another. So if we have the mechanical system which is converted to the electrical system through the electromechanical energy conversion device, then that system can be a generator or a motor depending upon the flow of energy from one form to the another. If the energy is converted from mechanical to electrical, then it is a generator. If it is converted from electrical to mechanical, then it is a motor. So a DC generator converts the mechanical power. So when we talk about the mechanical power, it is the product of torque and the speed omega into the DC electrical power. Electrical power is the product of voltage into current. So generator converts the mechanical power into electrical power, whereas in motor we will be converting the power from electrical to mechanical form. Now, the same electromechanical energy conversion device is capable of converting either as a motor or a generator depending upon whether the input power is of what form, whether it is a mechanical form or whether it is electrical form. So same device can operate both as a generator as well as motor. Hence, the motor and generator action are reversible in nature. These electromechanical energy conversion generally take place through the magnetic field. So there has to be a magnetic field through which the energy conversion will take place. Now, the generators are basically used in the power plant, whether it is hydroelectric power plant, steam power plant, diesel or nuclear power plant, where the natural source of energy, which is the water, the coal, the diesel, is converted into mechanical energy, and this mechanical energy is converted to electrical energy with the help of the generator. However, the electric motors are basically used in the power industry as in the form of the machinery such as hammer pressing, drilling machines, lathe machines, shapers, furnace blowers, etc. As well as if you talk about the household appliances such as the refrigerators, fans, water pumps, toys and mixers, there also lot of electric motors are in application. Let us see the basic construction of the DC machine. A DC machine essentially consists of the following main parts. So what are the main four parts which comprise a DC machine? It will have a field winding, it will have armature core and armature winding, it will have a commutator, and it will have the brushes. Now let us talk about the field winding first, how the field winding is there. So this is overall construction of the DC machine, and the field winding is mounted on the pole core. So you will be requiring to produce the magnetic field. So there will be the poles. So we have the poles in the form of vented one, which is the north pole and the south pole. So if you take this one as the north pole and this one as the south pole, hence the field winding will be mounted on the pole core. So here we can see that the field windings are present on the poles, and they require to produce the alternate north and south pole. So this is an electromagnet. So this field winding which are present on the pole core, it will be producing the alternate poles, that is the north pole and the south pole. It forms an electromagnet which provide the main magnetic field. So the magnetic field is the main requirement which is produced by this field winding. When the current usually flow through the field winding to produce a magnetic flux. So magnetic flux is produced when the current is flowing through this field coil, and it is made up of copper wire. So field winding is one of the important part of the electrical machine. Now if we talk about the armature core and the armature winding, so here we can see the construction of armature. This is the full armature. So it is mounted on the shaft and rotate in the magnetic field. So armature is the one which is rotating in the magnetic field. So it will be mounted on the shaft of the rotor. The armature core is made up of laminations of sheet steel. So in order to reduce the hysteresis loss, we have to laminate the armature core, which is made up of sheet steel. The outer surface of the core is cylindrical in shape. So if we see the shape of the armature, it is basically cylindrical in nature, and it provides with a large number of slots into which the armature conductor are placed. So armature core, there will be slots present in which the conductors will be placed, and these conductors are placed in different forms which we will see. And the ends of the armature windings are brought out to the commutator segments. So if you see, this is a commutator through which the end connections of the windings are connected. So the third part, which is the important part, which is a commutator, it is used for collecting the current from the armature conductors. So armature conductors, the end terminals will be in the slot of the commutator, which will be collecting the current which is coming from the armature conductor. These commutators are made up of a number of weight-shaped segments of copper. So it is made up of copper, and some segments are there which are insulated from each other by thin layers of mica. So mica insulations are present between the two segments. Each commutator segment is connected to the armature conductor. So armature conductors are present in the segment. The segments are insulated with mica insulation, and they are connected to the armature conductor. Now this commutator function is to convert the AC current which is induced in the armature conductor into unidirectional. Unidirectional means DC current across the brushes. So the main function of the commutator is to convert the AC current into the DC current, and the current is basically produced in the armature conductor, and these armature conductors are present in the slots or the segments of the commutator. Finally, we have a brushes which collect current from the commutator and supply to the external circuit. So in the internal circuit, where the current is produced in the armature conductor, it is given to the commutator, and we will be having a DC current. This DC current is given to the external circuit, which may be a load, through help of the brushes which will be collecting the current, and it is made up of carbon brushes. Usually 2 brushes will be there for a particular machine. Now what are the types of the armature windings? So armature windings depend upon the manner in which these armature conductors are connected to the commutator segments. There are generally 2 types of armature winding which are very famous. One is the lap winding. So the first type of armature winding is the lap winding. So what is a lap winding? Lap winding is a winding in which the armature conductors are connected in series through the commutator segments. So in the commutator segments, these armature windings are present, and these armature windings are connected in series in such a way that the armature winding is divided into as many parallel paths as the number of poles. So this is the most important thing to be remembered in lap winding, that the number of parallel paths in the armature winding is equal to number of poles present in the machine. So if we talk about that, if there are Z number of conductors and P poles are there, and there will be P parallel path in the machine, and each will contain Z by P conductor in series. So these series conductors are present in the commutator segment, which depends upon how many conductors are there, what are the total number of poles, and the formation of parallel paths. And then the EMF will be generated, which is equal to the EMF generated in any one of the parallel path. So if we talk about the total EMF generated, it will be equal to the EMF generated in the parallel path, because you know that in the parallel the voltage remains the same. The total armature current divides equally among the different parallel path. This is in accordance with Kirchhoff's current law, that when the parallel paths are there, the current will be distributed, and they will be distributed equally in all the parallel paths. And hence the lamp winding are generally used for low voltage, high current machines. So wherever the low voltage, high current machines are there, we will prefer the lamp winding. The second type of armature winding is basically the wave winding. And in the wave winding, the armature conductors are connected in series through the commutator segment in such a way that the armature winding is divided into two parallel paths irrespective of how many number of poles are there. So in the lamp winding, we have seen that the number of parallel path is equal to number of poles. So we can say that A is equal to P in case of the lamp winding, whereas in case of the wave winding, it is fixed, that is 2 in case of the wave winding. The number of parallel path is equal to 2 irrespective of the number of poles. Now here, if we have Z conductors in total, then only Z by 2 conductor will be in series in each parallel path. And the total EMF again will be the EMF generated in any one of the parallel path, and the total armature current will again divide in the equally between two parallel paths. So wave windings are generally preferred when the machine is basically high voltage and low current. Now here we can understand how the connections are being made in the lamp winding and the wave winding. So in the commutator, and where the segments are present, so here we have taken the example of 3 commutator segments, and these are the armature conductors which are connected to the commutator segment. So we can see that the end connection of the conductors of the armature are present in the commutator segments. So these coils, which are 2 coils, 2 conductors will make 1 coil, and these coils are connected in such a way that alternate north and south pole will be formed, and they will be connected in the commutator segments. So lamp winding and wave winding, where in the lamp winding the number of parallel path will be equal to the number of poles present in the machine, whereas in the wave winding the number of parallel path will be always equal to 2 as in wave winding. So why the name wave has been given? Because it is always flowing in the form of the wave ahead direction, whereas in the lamp winding we will be seeing that once it is forward, then again it will come back like this. So it will come back and then it will move forward. So classification of machines. So how do we classify the machines? We classify the machines depending upon the method of excitation on the field winding. So we have the field windings, and these field windings are given the current so that the magnetic flux is produced, and depending upon how this current is being given to the field winding to produce the flux, there are basically 2 classes of the machines. The first class is known as separately excited machines, where the field winding is provided with a separate DC source to supply the field current. So we can see that this is the field winding, and this field winding will be given a separate DC source which will produce the flux. And these flux will be cutting the armature conductors of the machine, and hence an EMF will be produced in the machine. Whereas in the self-excited machine, we will be seeing that no separate source are present, and it is the field current is driven by the own EMF generated. So the machine itself will be generating the EMF which will drive the machine. No separate DC source will be present in the machine, and this EMF will be produced at the armature terminals when the machine is working as a generator. So the self-excited machines are again further subdivided into 3 types depending upon the way the field winding is connected to the armature. So these are the 3 types, whether it is shunt wound machine, series wound machine, and compound wound machine. So 2 basic classifications of the machines are separately excited and self-excited depending upon whether the DC source is present or not. And in the self-excited machine, the machines will be divided into shunt. Shunt means parallel. We have a series wound machine and compound wound machine. Why compound? Because both series and shunt will be present. Let us see first the shunt wound machine. So this is the armature of a DC machine, and this is the field winding. The name shunt has been given because the field winding and the armature both are connected in parallel. So field winding is connected in parallel with the armature, and here the number of turns in the field winding, here the number of turns which is present in the field winding is basically, it will be 300 to 1000. If you talk about the series wound machine, so the field winding is connected in series with the armature. So it will be connecting with the series of the armature, and here the number of turns are basically 2 to 10 turns of the field winding. Field windings will have to carry the heavy current, so cross section to carry the large armature current. So whatever the current is generating from the armature, the same current the field winding is carrying. But however, here whatever the current is being generated from the armature, it will be divided into two different paths. One path will be going to the load and one path will be going to the field winding. So here there is no separate DC source. The field current which is flowing through the field winding will be producing the flux, and this field winding is produced due to the armature itself. So it is known as self-excited machine. Now in case of a compound wound machine, the machine will be carrying both the shunt field as well as the series field, and depending upon that it will be classified as long shunt and short shunt depending upon the direction of the current flow in the two type of field winding. So we can see the long shunt compound machine where the field winding is connected across the entire terminal of the load. So here we will be connecting the load, and if the field winding is connected across the load of the entire machine, so this is the armature and this is the series field winding, then that is known as long shunt. However, in the short shunt machine, we can see that the field winding is connected only parallel across the main armature, whereas the series field winding is outside the armature, and here we will be connecting the load. So both the shunt field winding and series field winding are generally wound on the same pole. So this shunt and series will be present in the same pole of the machine. So compound wound machine will have the advantage of both the shunt and series because it is carrying the shunt field winding as well as the series field winding. Now we will see the EMF equation of the generator or the motor. Now let us see the nomenclature first. We will discuss that the phi indicates the flux per pole and its unit is in Weber. So flux, this is notice that it is not the total flux, it is the flux per pole. The Z indicates the total number of armature conductors which are present in the machine. N indicate the speed of the armature in RPM, revolution per minute. P is the number of poles and A is the number of parallel path in the machine. So these nomenclature will be used to derive the EMF equation. Now when the armature complete one revolution, so the armature will complete one revolution, each conductor present in the armature will cut the magnetic flux which is produced by the field coil. So the field coil will produce the magnetic flux and the armature is rotating at a speed n and it will cut the magnetic flux. So the flux which is cut by one conductor in one revolution of the armature is equal to the flux per pole divided into number of poles. So phi is basically the flux per pole and P is the number of poles. So total flux cut by the one conductor is phi into P. Now time taken to complete one revolution. So this is our armature which is revolving at a speed n, and one revolution is completed at 60 by n second. So the average EMF which is induced in one of the conductor is equal to the flux cut by the time taken, which comes to be flux is the total flux which is phi into P. 60 by n is the time taken, so it is phi p n by 60 volt. Now this is the average EMF, and the induced EMF, which is basically the RMS EMF, if we see, so that is the resultant EMF per current parallel path. So average EMF per conductor multiplied with number of conductors in series per parallel path is phi p n by 60, which we have got here the average into Z by A, that is the total number of conductors which is divided into parallel path. So we'll get the famous EMF equation as phi Zn by 60 into P by A. This is the EMF equation of the DC machine. So in case of a DC generator, this EMF equation is known as generated EMF of the armature. So here we have the armature and G stands for generator. So these are the two brushes which are present in the machine. So whatever the EMF is generated here, that is given by Eg, and this Eg depends upon the flux per pole, the total number of armature conductors, the speed at which the armature is driving, P is the total number of poles, and A is the number of parallel path, which is dependent upon whether the winding is lap connected or whether the winding is wave connected. However, in case of a DC motor, the equation of this EMF opposes the applied EMF, hence it is called back EMF. So whether we are talking about the generated EMF in case of a generator or back EMF in case of a motor, both equation remains the same, only the name is different. Now let us see the voltage current relationship in case of different type of machines. Now in a generator, when the machine runs, then the generated EMF must be sufficient to supply the terminal voltage. So generator will be converting the mechanical energy to electrical energy. So here in the generator armature, the EMF will be produced, which is Eg, the generated EMF, and at the load terminal where the actual circuit is there, the voltage will be, terminal voltage will be V. So the generated EMF must be sufficient to derive the load voltage, and there will be some amount of drop which is present in the circuit. Now let us take the example of a shunt generator. So in the shunt generator, the armature of the generator and the field windings are connected in parallel, and the current which is produced in the generator will be distributed in two different paths in accordance with Kirchhoff's current law at this node, and the field winding will carry the current IF, which will be producing the flux phi, which will again cut the armature conductors present in the generator. The current which is flowing through the load is IL, and here we have the load resistor RL, the terminal voltage is V. So if we see that the voltage V is across the load and it is in parallel with the generator as well as the load, so here also the voltage will be V only. The field current will be equal to V by RF in accordance with the Ohm's law. And in accordance with the KCL, Kirchhoff's current law, we will be having the armature current is equal to the load current plus the field current. And in accordance with the KVL, Kirchhoff's voltage law, we can write that Eg is equal to V plus IaRa. So this IaRa is the drop. This IaRa is the voltage drop across the armature, and Eg is the generated EMF in the armature and V is the terminal voltage. There will be one more drop which can be taken included, which is the brush drop if it is present. So brush drop usually we take 1 volt per brush, so total voltage will be 2 volt here in the brush. So this shunt generator, generally it is applicable in ordinary lighting and power supply as well as in the charging of the batteries. Now let us take the example of a series generator where the field winding is connected in series with armature. So entire armature current which is produced by the generator, the current will be flowing in the same circuit in series, whether it is in the series winding or whether it is in the load coil. So the terminal voltage will be V. So here the current remains the same because it is in series. So armature current is equal to series current is equal to load current. And in accordance with KVL, we will see that Eg is equal to V plus the drop. This is the total drop, voltage drop. So here the total resistance will be added up. The resistance of the armature and resistance of the series field wind. Series generator are generally used in the distribution system as the boosters where we need to increase the voltage. Now let us take the compound generator. The first category is the short shunt. In the short shunt, we will see that the series field winding RAC will not be a part of the armature and the field. So these two will be connected in parallel. So here the shunt field winding will carry the current IF, and the armature current will be distributed in two different paths. So we can say that the series field winding and the load current will be equal. The armature current will be distributed in the load current plus the field winding. This is in accordance with KCL. If we talk about what is the field current, so field current, if we talk in accordance with the Ohm's law, so we will see that the voltage here in the field winding, here we have the terminal voltage V. So the drop across the series field winding will be ILRAC. So that will be added up, V plus ILRAC divided by RF will give you the field current which is present, field current which is taken by the RF. And in accordance with the KVL, Kirchhoff's voltage law, we can say that the generated EMF is equal to the terminal voltage V plus the drop of the armature plus the drop of the series field winding. So this is the KVL equation which we have applied in this particular loop. Now, if we talk about the long shunt machine, in the long shunt machine, the total field winding will be coming in parallel with the entire machine as well as the load. So the armature current here, we can say that the armature current is equal to the series current, which is same, because whatever the current will be coming here, the same current will flow in the series field winding, and then it will be distributed in the field winding and it will be distributed in the load winding. So IL plus IF will be the armature current, and the field winding will be V by RF, because here the terminal voltage is V. So same voltage will come here across the RF, and this is in accordance with Ohm's law and in accordance with the KVL, Kirchhoff's voltage law. EG is the generated EMF, V is the terminal voltage, and the total drop in the machine will be equal to RA plus RAC, that is the total drop due to armature and the series field winding multiplied with the armature current. So these compound wound machines are basically used in the lamp load, the heavy power services such as electric railways and the arc welding. So we have distributed this short shunt and long shunt machine, which are the compound generators. In case of a motor, only the direction of the current or the energy will reverse, otherwise everything will remain the same. Means now here we have the motor which is having these brushes. So motor will convert the electrical energy to the mechanical energy. So here instead of the load, we will be having the supply, the main supply B. So this will be taken to the motor. So earlier here the load was there, now we will be having the voltage, and hence the applied voltage V across its terminal must be sufficient to overcome the back EMF. So here the generated EMF will convert to back EMF in the case of the motor. So V has to be more than EB, then only the motor will be derived. Let us take the shunt motor first. So in the shunt motor, the terminal voltage V will be giving the current IL, which will be taken by the armature of the motor IA, and there will be some current which will be taken by the field. We can see that in the generator the current is flowing in the reverse direction. So the first field current we can obtain in accordance with the Ohm's law, and then we can obtain the current which is flowing through the armature in accordance with the Kirchhoff's current law, and then we can say accordance with the KVL as what is EB and V relationship. So the drop is IARA, where RA is the resistance of the armature conductors present in the motor. Now these shunt motors are generally applied in the lathe machine, the centrifugal pump, and the blowers and the fans. Let us take the series motor. In the series motor, the field winding again will be in series with the armature. The supply voltage V will be giving the current IL, which will be same current will be flowing here. So the current remains the same whether it is in the armature, series field winding, or the supply current, and in accordance with KVL we will be getting the back EMF EB is equal to V minus the total drop in the machine, RA plus RS. So these series motors are applied in electric locomotives, the cranes and the hoist pump and the conveyors. So series motors are generally used in high torque applications where we need to drive a very heavy load. Let us take the first compound motor, that is the short shunt. So the series field winding will be separated out from the entire armature and the field coil. So we can say that the current which is coming from the source is distributed in the armature and it is distributed in the field coil. So the series current is equal to the current which is taken from the source. The armature current is equal to IL minus IF. This is in accordance with Kirchhoff's current law. And the current which is flowing through the field winding in accordance with the Ohm's law, we can say that if the terminal voltage is V, then we have to take out the losses which is there in the series field winding. So we will be getting the Ohm's law V minus IL RS divided by RF as the field current. And in accordance with the Kirchhoff's voltage law, we will get the values of the back EMF EB is equal to V minus IARA, that is the drop in the resistance of the armature, minus ILRS is the drop across the series field winding. If we talk about the long shunt, where the field winding and the entire armature and the series field winding are in parallel. So the current which is coming from the source IL will be distributed in the current of the series field winding and the main field winding. So IA is equal to IS, which is equal to IL minus IF. And this is in accordance with KCL. If we talk about the IF, which is in accordance with the Ohm's law, so V is the terminal voltage, and hence the same voltage V we will be getting in the resistance of the field. So the voltage, supply voltage will be same because it is in parallel, and hence the field winding will be V by R. And in accordance with the KVL, the EB will be equal to V minus the total drop which is due to the resistance of the armature plus the series field winding. The applications of compound motors are used which take the advantage of both the shunt motor and the series motor. It is used in elevators, conveyors, rolling mills and the air compressors. Now if we summarize the entire formula what we have studied, so all the useful formulas are here. Now the generated EMF or the back EMF is given by phi Z NP by 60A, and for the lap winding A is equal to P and the wave winding A equal to 2. For the shunt generator, series generator and the compound generator again divided into short shunt and long shunt. And when we talk about, this is for the generating action, this is for the motoring action. So here we have shunt motor, series motor, compound motor again divided into short shunt and long shunt. So all the equations governing the voltage current relationship for the generator and the motor are summarized, which we can obtain from using the Kirchhoff's current law, the Ohm's law and the KVL Kirchhoff's voltage law. So this complete the basic fundamental lecture on electrical machine for the first year BTech students. In second year, when we talk about the electrical machines in detail, we will cover the entire concept of electrical machines. So we have already prepared a playlist of electrical machines where the entire lecture is given in very detail. The next lecture we will discuss few problems, basic problems on these fundamental electrical machines. Thank you for now. See you in the next lecture.